Okay, let's do some examples. Say that you work as an engineer at Phillips Glass, a manufacturer of sheets of glass for various industrial applications. There are two different processes that you employ to produce sheets of glass, process A or process B. And let's say you want a fairly uniform thickness regardless of the process used. So you want to know if there's a difference in the two processes with respect to the thickness of glass sheets that they produce. You collect a sample of 41 sheets made using process A, and you find the sample mean to be 3.04 millimeters with a standard deviation of 0.124 millimeters. When you collect a sample of size 33 sheets using process B, these sheets produce a sample mean thickness of 3.12 millimeters and a standard deviation of 0.137 millimeters. Let's find a 95% confidence interval for the difference in mean thickness for these two processes. And let's assume that the standard deviations are roughly equal to each other. Okay, so let's figure out what we know from this problem. Okay, we went out and we collected a sample of size, let's do this here, a sample of size 41 sheets from process A, and we found that the mean thickness from that process was 3.04 millimeters, and the standard deviation was 0.124 millimeters. Okay? So again, what we're doing here is we're just collecting a random and representative sample of the sheets of glass produced from process A. We're going to call that population 1. Okay? And we went and measured the thickness of each one of those pieces of glass, those sheets of glass, and we found that the average thickness was 3.04 from that sample, okay, with a standard deviation of 0.124. And now we go to process B. We're going to call that population 2. We collected a sample of size 33. We found that the mean thickness from those 33 pieces of glass was 3.12 millimeters, and the standard deviation was 0.137 millimeters. Okay? And we want a 95% confidence interval. Okay? So alpha here is going to be 0.05. Okay? Because we want a 1 minus alpha times 100% confidence interval, alpha must be 0.05. Okay? Other things that we know, in this confidence interval, we're going to use a t distribution because we don't know the population standard deviations. We're using S, our sample standard deviation, in place of sigma. So we're going to be using a t distribution. It has a certain degrees of freedom, and we want 0.025 alpha over 2 in each tail for this confidence interval. So what is the degrees of freedom? It is whenever we assume sigma 1 and sigma 2 are equal. We don't know them, but we assume that they're equal to each other. The degrees of freedom is n1 plus n2 minus 2. That is 41 plus 33 minus 2, which is 72. Okay, so we've got our degrees of freedom for this thing. We can plug that into here. So we're going to go look up a t-value associated with 72 degrees of freedom with 0.025 in the tail. Okay? If we go try to find this in the t-table that's provided in the course, if we go look in any textbook, we're probably not going to find this exact t-value. Okay? We could go down to the row associated with the degrees of freedom. We're not going to see 72 provided in that table. So we're not going to get this exactly if we use the table provided. Probably the closest degrees of freedom it's going to have is 60, which is quite a ways off from 72. Okay? Probably too different that we don't want to estimate using just degrees of freedom 60. Let's use Excel to find this. Okay? So how would we find this in Excel? We use the t inverse function. Inverse t inverse, that's an n right there, t inverse. And what t inverse wants to read in is the two-tailed probability and then the degrees of freedom. Okay? The two-tailed probability. So Excel doesn't make this easy on us. We just want this one-tail probability, 0.025. Excel requires that we give the two-tail probability. Okay? We want this for our degrees of freedom 72. We want 0.025 in this tail, and that's going to correspond to 0.025 in this tail because of the symmetric nature of this distribution. Okay? But Excel doesn't make it easy. Okay? For us to find that number on this axis, we have to input the two-tailed probability. We have to take this thing and multiply it by 2. So we have to input 0.05. Okay? 0.05. It's clunky, but that's the way it goes. Okay? 0.05, degrees of freedom 72. And if we do that in Excel, we get the number 1.993. Okay? 1.993. So now we have the number of standard deviations away this margin of error is going to lie on either side of our point estimate. Okay? And so our confidence interval, like we just said, begins with a point estimate. The point estimate for the difference in means, okay, that's based on our sample. We're going to add to it and subtract from it t for 72 degrees of freedom, 0.025 in each tail, times the standard deviation of the sampling distribution for the difference in means. And that is n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared, all over n1 plus n2 minus 2. And we multiply that by 1 over n1 plus 1 over n2. Okay? So this is just arithmetic now. We've got all of this stuff over here. We just have to plug it in and get the arithmetic right. That's the key part, right? There are a lot of places to make a mistake in here, especially if you're doing this in a calculator using Excel. Getting all this right is not easy. You got to make sure to double check it. Okay, so let's start inputting things. 3.04 minus 3.12 plus and minus our value of t here, 1.993 standard deviations away. Okay, so we're adding to this and subtracting from this 1.993 standard deviations. And the way we calculate the standard deviation is with 41 minus 1 times 0.124 squared plus 33 minus 1 times 0.137 squared. All of that over the degrees of freedom, 41 plus 33 minus 2. And we're going to multiply this by 1 over 41 plus 1 over 33. Okay? Just arithmetic. Okay? We just got to go through this calculation. Very straightforward. And if we do that, we should get this. The lower bound is negative 0.019 up to negative 0.141 millimeters. Okay? So what does this say? This says that with 95% confidence, the difference in mean thickness for the pieces of glass produced by process A relative to process B, okay, A minus B, that difference in thickness is between negative 0.019 millimeters and negative 0.141 millimeters with 95% confidence. Okay? Both of these are negative. That suggests that with 95% confidence, the mean for population 2, or process B, is bigger than that of process A. Okay? This number bigger than this number with 95% confidence, because both of these have negative bound. Both these numbers are negative. The bounds are negative. So with 95% confidence, that difference is a negative difference. Okay? And always important to include the amount of confidence that we want to have in this result and the units. So one last time, this true population difference, the difference in the true population means, lies in here somewhere between these two bounds with 95% confidence.